So, Lawrence, you're pushing the idea that in some sense quantum mechanics is the most fundamental thing we have, and the whole randomness of it, though even it might not be fundamental. Now, to me, as a skeptical empiricist, experimental astronomer, quantum mechanics is a prime example of a theory that theorists would never have come up with by themselves. The data was overwhelming for 100 years before any sort of theoretical framework comes by, and
Absolutely.
quantum mechanics still has really deep... Even the basics of quantum mechanics, like the two-slit experiment, really is very hard to understand in any philosophically
no one can
coherent
understand
way.
quantum mechanics. Really, we can't intuitively understand it.
So let's imagine that a grand unified theory... Let's imagine we didn't have any experiments. Let's say that the quantum mechanical scale was at another 50 orders of magnitude smaller than it really is. Then we would never have discovered quantum mechanics. There's no way a theorist would have come up with it. What if, as we push back to the very, very early universe, not merely the era of inflation, but maybe another 100 orders of magnitude earlier than that, there is something new coming in. Almost every time in the history of science when we've pushed way beyond, like we had good old Newtonian physics that worked perfectly well for things weighing a few kilograms, travelling a few meters per second, like me on a bicycle, and then it broke down either when we got very fast or when we got very small. We now have the laws of quantum mechanics, which work for everything we can explain, down from scales of 10 to the minus 20 of a meter up to the universe. But let's say if there could well be more laws of physics coming in on much smaller scales, is this possible? And would we ever know? And what could we do if that's the situation?
The answer is we don't know. That's what's great about being a scientist. You're allowed to say you don't know. And that's what makes science worthwhile, because you don't know, and that's why you keep looking. It could be that there's an ultimate theory of everything, and we'll understand it. I'm skeptical of that as a theorist. It could be, as Feynman said, that the universe is like an onion, that we keep peeling it back and discovering new layers. That's not a defeat. That's all we want to understand is a little bit more about how the universe worked. We may never have an ultimate understanding of everything, but that's okay. We keep, as my friend Frank Wilczek says, it's okay. I just want a theory of something. So, and it may be the case, and we just don't know the answer. And I will agree with you as a theorist that ultimately, we theorists can push back, but it is inevitably experiment that drives our thinking. Feynman said, science is imagination in a straitjacket. And that's what it is. The straitjacket is provided by experiment, and it's not even usually a straitjacket. It's actually a window, because it allows you to look to places you never thought you'd see before.
So if we did find, let's just say there is a theory of everything, and we found it, do you think we would ever know we found it?
It would have to have certain characteristics that I think theorists would argue, and it's a little technical to talk about, but I can imagine a theory of everything that would be unambiguous. However, I can imagine many theories of everything that would not be unambiguous. And so, we'll just wait and see. We'll wait and see. The excitement for me as a theorist is that we are closer to being able to empirically address questions about the universe on all of its scales than I would ever imagine when I was a graduate student. And the surprises that have taken place have been unimaginable, and I fully expect that the biggest surprises will be in the future. And in fact, every day I wake up and I'm surprised if I'm not surprised.
Let's look at where the future of astronomy might go. So let's imagine that we get lucky with the Large Hadron Collider and we discover some evidence for supersymmetry. And let's imagine we also get lucky with the gravity wave data and the microwave background. And so that between those two, we can hopefully nail down the era of inflation. But where do we go from there? Let's say we've got inflation nailed down and we work out all the various consequences of that. That gets us back to maybe 10 to the minus 40, 10 to the minus 50 per second, the Planck time. But where are we going to go beyond that? There's nothing more to get out of the microwave background. The microwave background, at that point, we've only got one universe.
It could be that the era of it wasn't always the case that astronomy contributed to fundamental physics. There have been various times. It could be that astronomy and cosmology become trying to understand the later evolution, how things formed. A theory of everything really isn't a theory of very much, as one of my colleagues has said. We still wouldn't explain how oatmeal boiled. And you'd have to... There's a lot about the universe that even if you had a fundamental theory, that you need to understand. Why do black holes form before galaxies? And if so, why? And what relationship do they have to galaxies? But also, so we may nail sort of in some of the physics of the early universe, there's still the open question of dark energy. It could be, although I'm pretty convinced as a theorist, we're not going to learn more about it than we now know, which is not very much. But it could be that we discover, by extending the kind of observations we've made, that the dark energy of the universe is changing. And that would be a profoundly important discovery with impact for the future and impact for particle physics. So we don't know what new things we're going to see that will. It could be that there's something else that will change our picture of the early universe. We just don't know. We do know when we think about the future, and I've thought a lot about the future as well as the past and written about it, that if the universe we live in, if the dark energy is constant, then we live in the worst of all possible universes for the future of life as far as I'm concerned. And I find that very heartening, not disheartening. But the expansion of the universe will continue to accelerate, and in a time which is measurable. And in fact, there'll be stars. There'll still, in 2 trillion years, there'll still be main sequence stars around in 2 trillion years. There'll still be potentially organic material and astronomers and powered by solar radiation that can look out at that universe. What will have become our Milky Way galaxy after it merges with all the other galaxies will be one in our region, will be one large galaxy. We'll look out and see nothing. All the rest of the galaxies in our universe will have disappeared because they'll all be moving away faster than the speed of light, which is allowed by the laws of general relativity. And for me, I find that very poetic because the observers then will imagine a picture that we had of cosmology 100 years ago. Remember, before Hubble, astronomers thought, first of all, that our universe was constant in time, that there was one galaxy, our Milky Way, surrounded by an eternal, empty universe that had been around forever and would be around forever. In the far future, 2 trillion years, it could be that astronomers arise, do everything they can do, discover electricity, magnetism, quantum mechanics, go out and measure and see exactly that, a single galaxy surrounded by empty space. Eventually, of course, they'll die, the stars will collapse into some massive black hole, which will, in principle, evaporate. The universe will become cold, dark, and empty, and that's the future. And as my friend Christopher Hitchens said when I've talked to him about that, and says, well, the answer to the question, why is there something rather than nothing, may be, just wait, there won't be for long. But that's the future as it might be, as Charles Dickens would say.
That's sort of the most likely future given what we know now.
Given what we know now. But as I'm happy to have said that I've also written a paper with my friend Mike Turner that shows that we really can't, we really never know no matter what observations we make, it's impossible to know what the future will eventually be, because it turns out, let's say the dark energy that Brian discovered is really not there, it's a mistake. Okay? It's it's a big mistake. We apologize. But it turns out, you might say, well, then we know the future because Einstein told us a closed universe will collapse and an open universe will expand forever, etc. Well, it turns out there could be a dark energy which is much smaller than Brian could have ever measured, and there still may be one. So even if that dark energy goes away, there could be another one. So even in that case, an open universe can collapse, a closed universe can expand forever. And it turns out, unless you have either a theory of everything or an infinite number of measurements, the future is uncertain. And that cosmic mystery, for me, is very enlivening, because it's the search rather than the knowing that, for me, gives satisfaction.
So let's talk about some of the extreme ends of the universe. So we've talked about that the cosmological constant is more or less constant. And so within 100 billion years, the nearest galaxies will be so far away, you wouldn't know they're there. Our stars of the Milky Way will last for much longer than that. And those stars will die. You will end up with white dwarfs orbiting each other. A lot of them will eventually coalesce to form a black hole. Some will evaporate off. So do we end up with everything being a black hole and evaporated little stars on their own? Presumably, if you're a little star that gets flung out, you're sort of all on your own some. And so you're actually not a black hole. You're a white dwarf out on your own.
And there will be stars that are ejected from our galaxy. In fact, I wrote a book called Atom where it involves such a star.
Yep.
But even those may have a bad future, because it's true. If that's the case, then there will be dead lumps of matter, which will be almost infinitely far apart.
Yep.
So they don't mean much, but they'll still be there. But if our ideas of grand unification are correct, it's worse. Because remember, protons decay. And eventually, if it's true, it's just like literature. Beginnings and endings are often tied together. The proton decay and the physics of the early universe are responsible for why we're here. But they may be responsible for its demise as well. Because if protons decay, then the protons in those white dwarfs will decay. And eventually they'll produce radiation which will dissipate. And the universe really will become cold, dark, and empty.
But on the other hand, we don't understand dark energy, and so, as you've already said, it's very hard to predict what we call dark energy might be. It might suddenly go through a phase transition and turn into something that's very attractive and reverse what's going on.
It could be that. It could destroy everything we see. Yep. I'm very happy to say that when I was working here at ANU last summer, I came up with a model which saved the universe. It's probably wrong, but it actually, we could show that there's a kind of dark energy that would decay that would be imperceptible. If it decayed and produced stuff, we'd never notice it here in the studio, and so it would allow us to survive and keep asking questions. We just don't know the answer.
So what's the time scale that the universe can change directions from what it's doing right now? I mean, can it do it in an impossibly short amount of time if it wants to?
Well, it could. It could be impossibly short, because there could be a phase transition that if it happens at the speed of light, everywhere. Yeah. So it could be that the field decays and everything changes before we finish this question. Yeah, yeah. It's a sentence. Barring that, we know that the dark energy isn't classically changing very fast. We know that from constraints from observations. So unless there's some quantum change like that, a phase transition, the universe will continue to go on as it is now for at least probably 100 billion years.
So what about the idea, since we haven't measured the equation of state of dark energy, what happens if it is below -1?
Yeah.
So this is dark energy that becomes more and more dense over time as the universe evolves.
Yeah. Now, I have to say, as a theorist, I know you love to talk about it. As a theorist, it's even uglier than quintessence. It's sort of
certainly ugly, yes.
Ugliest to the, it's exponential of ugliness.
Yes.
Because there's no, and I repeat, there is no fundamental theory, particle physics theory, that allows an equation state less than -1. It violates pretty well most of the rules that we know about nature. But if it's true, that means the universe ends at a finite time, because the dark energy right now, the acceleration of the universe isn't affecting you and I and the three of us in the studio. Okay? It's so small that we're not accelerating along with it. But if the dark energy density increases, then that repulsive force will increase. And right now it's sort of accelerating the universe. If it increases, it'll eventually cause the force will be large enough that repulsive force will beat out the attractive force of our galaxy, gravitational force, break apart our galaxy. If it continues to increase, it'll break apart stars. Continues to increase, it'll break apart planets. Eventually it'll break apart atoms, and in a finite time there'll be this big rip, and literally everything, including the fabric of space, will break apart, and then we'll have to understand what quantum mechanics brings. It's a very poetic picture, but it is highly unlikely.
But yeah, I kind of like it, because you end up with an exponentially expanding universe of almost infinite density, which kind of sounds like how we were born. It's almost a rebirth, isn't it?
Well, well, in a way, maybe. But I mean, what the great thing about the universe, Brian, is that it doesn't give a damn what you want or what I want. Yeah. And so we'll just wait and see.